Welcome to The Explainer. Today we're jumping right into a topic that perfectly blends high-level atmospheric physics with the everyday technology buzzing right over our heads. We're going to dive deep into the actual flight mechanics of multi-rotor drones and figure out what really keeps these machines in the air. It's an absolutely fascinating subject, so let's get started.
Going into this, it's super easy to assume that if you understand how an airplane flies, you automatically understand drones. But our sources highlight that moving to rotary wing systems requires a total paradigm shift. Drones are constrained by what's called disk loading and the incredibly intense nonlinear power requirements of hovering. It's a completely different aerodynamic beast.
Okay, let's dive into this. Here is our structured roadmap for today. We'll start with exactly why drones aren't airplanes, tackle the thin air problem, break down the physics of hovering, and explore the highly counterintuitive U-shaped power curve. Then we'll apply all of this to maximize real-world flight time and finish up with a head-to-head comparison of sea level versus altitude.
All right, Section 1. Drones are not airplanes.
While the principles of fixed-wing airplane performance give us a helpful baseline, a multi-rotor demands a highly specialized approach. Think about it. A fixed-wing aircraft relies on forward momentum over large wings to generate lift efficiently. But a drone's operational envelope, that is dictated by entirely different factors. We're talking air density, thrust-to-weight ratios, and battery discharge rates. Because the drone spends so much of its time just hovering, which takes massive energy by the way, its performance limits are mathematically tied to its battery drain in a way that airplanes simply aren't.
Moving right along to Section 2. The thin air problem.
So according to the 1962 U.S. Standard Atmosphere data, drones are incredibly sensitive to density altitude. The air density directly affects the thrust produced by every single propeller. If you track the numbers all the way down to the 10,000-foot mark, the density ratio drops significantly. To maintain the exact same lift at 10,000 feet that it had at sea level, a drone's flight controller has to drastically increase the motor RPM just to compensate for that much lower air density. Let's actually anchor this concept by looking at 5,000 feet. At a 5,000-foot altitude, the density ratio is exactly 0.8617 compared to sea level. That means the air is quite literally almost 14% thinner. You kind of have to imagine the air as a fluid that the drone is swimming through. At 5,000 feet, that fluid is substantially less dense. So the propellers literally have less material to push against to generate thrust. And this thin air causes a genuinely fascinating instrumentation problem. Many drones use an onboard pitot tube to sense indicated airspeed, but because the air is so thin at altitude, the sensor gets tricked. It reads a lower speed than reality. Your true speed through the air is actually much faster, meaning high altitudes are secretly devouring your battery consumption while your sensors just play dumb.
Which brings us to Section 3. The physics of hovering.
Hovering is essentially the rotary wing equivalent of straight and level, unaccelerated flight. And this brilliantly illustrates momentum theory. See, the thrust produced by a rotor comes directly from the momentum change of the air. The mathematical formula for induced velocity, which is just the speed of the air passing through the rotor disk, places the disk area of the propeller in the denominator. So this mathematical law proves a really surprising fact. Increasing the rotor's area actually reduces the power required to hover. Bigger props literally equal a more efficient hover.
But of course, hovering isn't exactly free. The total power required for a drone is the sum of three distinct mechanical hurdles. First up is induced power, which is the raw energy required to actually produce lift. Second is profile power, the energy needed just to overcome the aerodynamic drag of the physical blade spinning through the air. And third is parasite power, which overcomes the drag of the drone's physical body itself, mostly when moving forward. The sum of these three specific powers dictates the total electrochemical energy being aggressively drained from your battery every single second you're in the air.
Next up, Section 4. The U-shaped power curve.
Now, what's really interesting about this curve is how it completely defies standard logic. At zero airspeed, so a basic hover, the power required is incredibly high. But as the drone starts flying forward at a moderate speed, the power required actually drops. This dip forms a U-shape due to something called translational lift. The drone essentially outruns its own turbulent downwash and bites into fresh, clean air, making the rotors much more efficient. But then, as you continue to speed up, that third hurdle we mentioned, parasite drag on the drawn body, spikes massively, driving the power requirement right back up.
If we translate this U-curve into practical, everyday piloting, it gives us two absolutely critical speeds. The lowest point, the absolute trough of that U-shape, is your minimum power speed. Flying exactly at this speed will keep you in the air for the maximum amount of time. However, if your goal is to cover the maximum physical distance over the ground, you need to fly at the maximum range speed, which is always slightly faster than the minimum power speed. Choosing between these two depends entirely on what your mission requires.
All right, moving to Section 5, maximizing drone flight time.
Well, maximizing time actually starts the exact moment you leave the ground. Taking off isn't just hovering. It requires vertical acceleration from zero. Our sources show that for vertical takeoff dynamics, industrial drones are specifically designed to maintain at least a 2.0 thrust-to-weight ratio. Having double the thrust required just to sit there is a vital safety margin needed to overcome the massive initial current draw when you're trying to break gravity's grip.
Once airborne, we rely on a modified version of the classic Breguet logic for electric drones. It proves that your total endurance, meaning your flight time, is a massive balancing act. It's simply your battery capacity times voltage times system efficiency, all completely divided by the power required. So the crucial point is that your rate of climb and total mission time are mathematically bound to this equation. If you want more time in the air, you either need to pack a bigger battery or you need to drastically shrink that power requirement on the bottom of the equation.
And how exactly do you reduce that power requirement? By utilizing that U-shaped curve. Our sources highlight a truly fantastic fact. Flying at the minimum power speed, that sweet spot at the very bottom of the curve, provides a 15 to 20% endurance boost compared to just hovering. Let that sink in for a second. Standing perfectly still in the air is actively punishing your flight time. If you really want your battery to last, you actually need to keep moving forward at that optimal speed.
Finally, Section 6, sea level versus altitude.
Let's set the stage for a quick case study. We're looking at a performance assessment for an industrial drone that weighs exactly 15 pounds, and it's equipped with 4 15-inch rotors. We're going to see what happens to the math when we take this exact setup from a comfortable, dense sea level environment all the way up to the harsh, thin air at 5,000 feet.
Here is the defining number, 7%. Because the atmospheric density drops to roughly 86% of sea level at 5,000 feet, the physics of momentum theory and induced velocity demand more energy. Our calculations showed that this specific drone requires approximately 7% more power just to maintain basic hover stability. That extra 7% power draw means a significantly higher current is being pulled from the battery every single second, which severely slashes your total mission time compared to a standard sea level flight. This absolutely proves that altitude and disk loading aren't just minor variables to brush off. They are the ultimate constraints of multi-rotor flight. We've seen how thin air forces your motors to work overtime, how hovering drains your battery faster than forward flight, and how mastering that U-shaped curve can literally buy you 20% more time in the air. So, I leave you with this. Next time you fly, will you let the atmosphere silently dictate your mission, or will you use physics to master the power curve? Thanks for exploring this with me.